Hi students, and welcome to Preliminary Chemistry and the Metals video series. In this particular video we're just going to really introduce the concept of periodicity and some of the important properties that demonstrate this property of periodicity, and we're actually going to investigate these by doing some graphing exercises in class. So let's just contextualize this first of all by identifying the important levels of organization in the periodic table. Firstly, the periodic table we now know is organized by atomic number. So hydrogen is number 1, helium is number 2, and so on. There are 7 horizontal periods, and it's sometimes a little bit difficult to see that because the lanthanoid and actinoid series are sitting below the table, where in actual fact they should sit in a position within the table that would actually make the table much longer. To avoid that, we've removed them and we put them down at the bottom and kind of indicate where they would go. There are 18 vertical groupings or columns, and each of these groups represent the different families of elements, and some consistency is what we see when we look at the different families in those groups. The atomic weight, or often denoted by the letter A, is the listed weighted average of all of the naturally occurring isotopes for that element. So that is why atomic number is a whole number, 1, 2, and that's always equal to the number of protons. So it's always going to be a full whole number, but the atomic weight is often listed to several decimal places, and that is because it is a weighted average. Basically, all of the different naturally occurring isotopes in their proportions are added together and to give us an average weight for the individual element. And that's why those ones don't round out very easily. So when we're looking at the groups in the periodic table, we know there's 7 periods, and we kind of get a sense that that's actually related to the shell or energy level that's being filled with electrons. But as far as the groups are concerned, there's a couple of these that have some more common names that it's useful for you to start to be aware of. Firstly, the group 1, or the first group of elements, are the alkali metals. These are very reactive metals with generally a lower density and a valency of +1. The second group along, so the alkali metals include things like lithium, sodium, potassium, and francium. The group 2 elements are the alkaline earth metals. So these contain things like calcium, magnesium, and also barium and so on. These are less reactive than the group 1 elements, although they are relatively reactive themselves, and they have a valency of +2 and they form ionic substances. If we use our own numeral system, then really the next groups are groups 3 to 12, and that's the group that spans that transition metal group in the middle of the periodic table. Most of these elements are metallic, hard, and they have much higher density than the alkali metals, and their valency varies from +1 to +4. There's a number of different reasons for that, most of which we don't need to worry about in this course. Beyond the transition metals, we either continue with our Roman numeral system, 3, 4, 5, 6, or we look at group 13, 14, 15, and so on. So if we look then at the first one past, group 13, boron is a semi-metal, and the rest of them underneath boron, aluminium, and so on, are metallic elements. They have a valency of +3 in ionic substances. The group 14 is the one that starts with carbon. Now, carbon is a non-metal. Silicon and germanium both classified as semi-metals, and the rest would be soft metals. These tend to have a valency of +4, and both carbon and silicon can be involved in those network covalent structures that we've talked about previously in the course. Group 15, or group 5, contains nitrogen and phosphorus, which are both non-metals. Astatine and antimony, which are semi-metals, and these have valencies of +3 or +5, depending on if they're acting as the cation, or also -3. They can form the anion in an ionic compound. In group 16, or group 6, we have oxygen and sulfur, as well as selenium, which are non-metals, and tellurium, which is a semi-metal. These tend to be more likely to have a -2
valency, particularly for ionic substances, but they can form +4 or +6 depending on the arrangement and which other atoms they're surrounded by. The group 17 are also known as the halogens. These are pretty much all non-metals, although astatine sometimes gets classified as a semi-metal, and their most common valency is +1, but again, they could also have a +7 valency. And the last group, the group that are at the extreme right of the periodic table, group 8 in the Roman system, or 18, are our noble or inert gases. They are stable, although we have some examples of some of these, like xenon forming or radon forming compounds, but they're very stable. They have a full valence shell, a full octet, so 8 electrons in their valence shell, and so therefore they do not tend to form compounds. The trends in the periodic table are worth having a bit of a look at here. I'm not going to go into them in a lot of detail because I'm going to get you to plot some of these in class to actually set up some graphs so we can see the periodic nature of many of these properties. But some of the ones that come up most commonly are electrical conductivity, and you can see that is going to decrease as we go across a period and increase as we come down the group. Likewise, the atomic radius decreases. This is for reasons of the fact that the nuclear charge gets stronger, more protons in the nucleus, so that pulls the electrons in a little bit tighter. And for equally obvious reasons, we're starting a new electron shell. It increases as we go down the group. And you can see patterns there for ionization energy, melting and boiling points, and electronegativity as well. Now, electronegativity is an interesting one. It's kind of the opposite of ionization energy. If ionization energy is the amount of energy required to pull an electron out of the atom, electronegativity is that ability to draw an electron into the atom. So we would find this is something that is very high for something like fluorine, which is right up the right side of the periodic table. Not so good, of course, for the metals on the left side. So as I say, we're going to plot some of these and set up some graphs in class that hopefully will give you an idea of periodicity and how these trends are observable both across the period and also within the groups. Thanks for watching.